So our next speaker is, final speaker is Bob MacDowall from Goddard Space Flight Center. References to LSSO. He will be telling us about radio observations, but more lunar science oriented from the lunar surface. Bob?
Okay, so this is the title for the abstract was Status of the Radio Observations at the Lunar Surface of Photoelectron Sheath Payload. Bill Farrell and Damon Bradley at Goddard are co-investigators for this NASA-provided lunar payload. Jack Burns is a collaborator. There are others, but these are the people I included with the abstract submission. So Rolls's, well, what is that? That's radio wave observations at the lunar surface of the photoelectron sheath. And so it's basically it's a radio frequency spectrometer with the frequency range 10 kilohertz to 30 megahertz using two overlapping frequency bands, 10 kilohertz to 1 megahertz and 300 kilohertz to 30 megahertz with the bandwidths that are indicated to make various observations with some focus on regarding the photoelectron sheath density. We will have 4 monopole stacer antennas, at least I hope, used as monopoles at 1 meter and 3 meters above the lunar surface. They are mounted on the lander orthogonally to help provide the directional source measurements. And here on the right is the commercial lander that will transfer Rolls's to the lunar surface. This is the Nova C lander provided by Intuitive Machines of Houston, Texas. And they've changed the landing site a couple of times, but now they're saying it's the Schroeter Valley or Vallis Schroeteri, which is, let's say, can I read that? Yeah, good. Is here. It's the largest, it's said to be the largest sinuous valley on the moon. So I just realized, just finding that out recently, I need to talk with them and to find out if they're planning on landing in the valley or next to the valley, which is located here to the north and west of the Earth-Moon line. On the lander, there's our mechanical electronics box is mounted here on the north side of the lander where it's a little cooler than the other sides. And each of the antennas is attached to a front-end electronics box. Here's one front-end electronics box at 1 meter from the surface. Here's one at 3 meters from the surface. The other one is back here, and the other one is behind the lander, so you can't see it. So and they will, of course, be deployed once the lander, the stacer antennas will be deployed once the lander comes down. So, let's see, did I use one sheet? Yes, here we go. I went 2 sheets, sorry. So for the lunar surface photoelectron sheath, Rolls's will determine the density only in the region sort of 1 meter to 3 meter above the surface. This is of scientific value, we say, and it's also important to determine the effect on the antenna response of some lunar radio observatories with antennas not lying on the lunar surface, which have been discussed. So in this plot on the right, which is a model from a simulation code by Andrew Poppe and Mike Harani, a paper 2010, for various solar wind environments. And you see that is a solar wind after a shock, after a flare, after a CME. So it actually changes the photoelectron densities at the surface. Anyway, for the typical solar wind, the density at 1 meter height is about 6 times 10 to the 7th meters per meter cubed, which corresponds to 70 kilohertz in the electron plasma frequency. And then as you go to 3 meters above the surface, the density goes down. And you see here on this plot how it goes down and flattens out for the various environments. And then Bill Farrell, who used that model in his paper for 2013, also used a different model from Zimmerman et al. 2011. And The reason I'm showing this is because you can see that these levels are rather different from what they were on the previous page. And there are slight differences at 1 to 3 meters. And we want Rolleses to provide the correct density and scale height for comparison to these models. And anyway, in this case, here we're talking about 5 times 10 to the 7th per meter cubed and 10 to the 7th per meter cubed for the photoelectron density on the surface, again, for the typical solar end. You can see that that's the black line here. So it goes down rather rapidly. When there was a CME, it was more than a factor of 10 higher, according to this model. Anyway, Rolleses will measure these values based on the thermal noise spectrum, on possible wave activity at the electron plasma frequency, and from attenuation of the radio spectra of remote radio sources at frequencies near the electron plasma frequency. And here's an example of what we expect we might see at some point. This dynamic spectrum of 24 hours of data covering 10 megahertz down to 100 kilohertz is from the WAVES instrument on the WIND spacecraft, which is out at the Solar Earth L1 location. And it has been there for a number of years, having been launched more than 20 years ago. So what it sees is it sees solar type 3 radio bursts on this day. It sees, even at that distance, it sees a lot of terrestrial auroral kilometric radiation. It also sees some radio frequency interference lines from transmitters on the Earth. And it sees Jovian radio emissions, all during this 24-hour interval on February 20th, 2012. And we expect that Rolleses will see all of these similar phenomena. And so we will see this with Rolleses for something on the order of 14 days, but it will be a little different than what WIND is seeing, as we'll see in a moment.
Bob, 2-minute warning.
Okay, gotta go faster. So anyway, so another goal will be to see if we detect dust impacts. In general, spacecraft in interplanetary environments, so orbiting planets, when they get struck by dust particles, which release electrons and ions from the surface, affect the surface photoelectron environment and create detectable electrical signals like this plot of the data from Cassini when it crossed the Saturn F-ring. So Rolleses may detect dust impacting the Nova C lander or the antennas in a similar way, but with our time resolution of 4 seconds, we won't detect one dust particle. We would only detect clouds of dust particles. Briefly, another thing we may detect is a reflection of incoming radio emissions from below the lunar surface. Previously, Apollo 17 surface electrical properties instrument on the rover made these measurements at 6 frequencies. There's a paper by Grimm and Icarus 2018 where he describes some recent analysis of those S&P results in detail. And it's particular because no deep interfaces were detected. The thickness of the torus littrow volcanic fill must exceed 1.6 kilometers or more. Well, there's no ground plane below the Rolleses antennas, so we might see radio waves that penetrate the surface being reflected, and that will provide interesting information about the structure below the lander. Very quickly, when the WindWave spacecraft flew past the moon in 1999, over a 24-hour period, this was the terrestrial transmitter producing radio frequency interference that it saw, compared to some relatively weak solar type 3 bursts, the vertical lines. So all of these horizontal lines are radio emission coming from transmitters on the ground. And we want Rolleses to determine what that looks like today in 2021. So I've already told you what the frequency bands are, but if you missed it, there they are. The band resolutions will be as shown. Spectral time resolution, as I said, will be approximately 4 seconds, alternating for each of the high and low spacers. We can't get more than 17 kilobits per second because the Nova C lander has so many payloads that that's our limitation. And then, in summary, we've talked about photoelectron density, which was the focus of the proposal. We've talked about these other scientific and technical observations that ROLSs will make. And we look forward to delivering ROLSs to intuitive new machines later this year, and then obtaining data from the lunar surface for a lunar day in October 2021. Thank you.
Okay, thanks, Bob. So I do see a question from my co-chair in the chat. Since I cannot do the conversion in my head, how do these photoelectron densities convert to plasma frequencies?
Well, it's basically the dominant electron population at the lunar surface, and well, it's evolving for various reasons. So there may be ways. It's not a guarantee. That's why we need several ways to determine the density. And as I said earlier, even though the antennas aren't that long, we might still be able to see the thermal quasi-thermal noise spectrum in the electron data, and we'll be looking at the attenuation of radio sources and using and working it so that we can calculate the density that's causing that attenuation. So there are several different ways that will measure the density of the electrons which construct the lunar photoelectron sheath.
I was wondering about the landing site. Was that chosen for any scientific reasons, or was that purely just from a landing perspective that site was chosen?
Actually, it was just, two things. This is the third site that Intuitive Machines has said they will be using, and that since they selected this relatively quiet, Hazel, since they selected this landing site recently, I haven't done research on it, but now, looking at the story of it in Wikipedia, I was stunned to realize that this was a valley, a large valley in that area, related to volcanic activity. And so I need to find out from them, are they really going to land in the valley? And if so, why? Well, they want to land they want to choose a site which is very flat and where there are not boulders that would impact the landing. But I don't know the reason. So I can once I get an answer to that question, I can forward it to you.
Okay, thanks. I don't see any other
You're welcome.
questions as of now. So thanks again for the talk, Bob.